Gears are vital components of the mechanical world, powering countless industrial and consumer devices we rely on daily. Take cars, for example. Gears in the transmission help shift speeds smoothly, transferring power from the engine to the wheels. In your printer, gears move the paper and position the printhead, ensuring clear and precise documents. Mechanical clocks rely on gears to keep accurate time, moving the hands at the correct speed. Among the many types of gears, spur gears are the simplest and most commonly used. Spur gears are a type of cylindrical gear with teeth that run parallel to the axis of rotation. They are the most common and basic form of gear, known for their simple design, durability, and cost-effectiveness. This gear type is used to transfer mechanical motion and power between parallel shafts, allowing for the control of speed, torque, and positioning. This transfer can be made by a compound train, where multiple sets of gears are arranged to transfer torque and rotational speed from one to another until the desired values are achieved. In this video, I will introduce you to a Python app designed to help you size a compound spur gear train based on torque and resistance requirements. All you need to do is set a few parameters. The total length of the gear train will be determined by the distance between the first and last shafts and the resistance requirements based on the selected material. Therefore, the app will generate a table detailing each gear's main dimensions, stresses, and safety factors. It will also display the gear train configuration, including each gear's identification number. Besides, the app will create a sheet with the coordinates of the gear's profiles, which you can use to create a CAD model for each one. Let's say you have an electric motor with a rotational speed of 70 RPM and a torque of 6 Newton meters, but your application requires a torque of 18 Newton meters for the shaft. Mechanical power is the product of torque and rotational velocity. Since the power source is the same, we can establish the following relation. From this fundamental relation, we can derive other equations that will help us determine the appropriate gear sizes. One important parameter is the pitch diameter, which, according to the AGMA standards, can be used to specify gear tooth dimensions based on the chosen pressure angle. Stresses can be calculated using AGMA's equations, which are based on empirical constants. The same applies to the fatigue strengths of the gear material. In this app, the face width of the gears is determined based on resistance criteria. Increasing the face width generally improves the gear's resistance to failure. However, according to Norton's machine design book, the face width is typically chosen within these limits. After considering all the design parameters, the code generates a spur gear train with the appropriate dimensions for each gear. The number of gears in the train might have increased due to resistance criteria, or because the number of teeth must fit within the gear profile constraints. Soon, I will create a video explaining how you can create a CAD model for each gear on Onshape. At the time of recording this video, the code I'm using, which you can find in the description, is in version 1.0.0. The code can be further improved to make it more efficient and accurate. If any errors are identified, they will be corrected. I'm open to any feedback and contributions from those who are interested in collaborating with the development of this code. Thank you for watching. If you've made it this far, please subscribe to the channel for more videos like this and visit my GitHub to explore other similar projects.